Hi there and welcome to this next video in our Integrated Math 1 video series. This is Unit 3, Lesson 1. And this unit is going to be focused on linear functions and everything about that. Before we get into our lesson for today and talking about linear functions, let's go ahead and do a warm-up for today. So try these 5 problems. Again, try to do them using mental math if you can, and then we'll talk about them here in just a second. Okay, so in number 1 here, we've got an arithmetic sequence here, and you can tell by looking at the explicit formula here that it's arithmetic, and it says write the first 5 terms. So what we could do is a couple different ways. We could insert 1, 2, 3, 4, and 5 into n and find out what each of those outputs. Or we could think about the explicit formula and what these values mean, and then think about it recursively, meaning how to do this every time, like how to get from one term to the next. So let's do it both ways. So let's first start by inserting 1 into here. So 1 minus 1 is 0. 0 times 2 is 0, and then 0 plus a negative 3 is just negative 3. So we're going to start with negative 3. All right, you can insert 2 here. 2 minus 1 is 1. 1 times 2 is 2. And then 2 plus a negative 3 is a negative 1. All right, if we insert 3 to get the third term, we're going to have 3 minus 1 is 2. 2 times 2 is 4. 4 plus a negative 3 is a 1. All right, and then to get term 4, we need to substitute in 4. 4 minus 1 is 3. 3 times 2 is 6. Minus 3 is 3. And then lastly, I take the fifth term. 5 minus 1 is 4. 4 times 2 is 8. 8 minus 3 is 5. And if you notice here, it's increasing by 2 each time, which is how we could have done it the other way. So if we think about what the explicit formula is, it's A1, this is the first term, plus the common difference, so what we're adding or subtracting each time as we go, times, and this is always in minus 1 in this particular form. So we have the first term and then what we're adding each time. So we could just start with writing negative 3 and then add 2 each time. So we wouldn't have to put in 5, 4, 3, 2, 1, all of those. So a couple different ways to do that one. What is the next term in this sequence? Let's see. Are we adding, looks like maybe we're adding 9 here. Oh wait, but that doesn't work here. So if you thought it might be arithmetic, it's not, because we're not adding the same value each time. Let's try geometric. Maybe we're multiplying by the same value each time. And then let's see, negative 3 times negative 2 would be 6. 6 times negative 2 would be negative 12. Times negative 2 would be 24. And then 24 times negative 2 would be negative 48. So that's the next value in that term. So this is actually a geometric sequence. If you remember from our last unit, we talked about geometric sequences a little bit. We ended up talking about the explicit formula for this, which would be a sub n equals the first term, which is negative 3, times the common difference is negative 2 to the n minus 1 power. So we briefly talked about that a little bit last unit. We'll talk about it even more a few units from now when we get to exponential functions and geometric sequences a little bit further. Number 3, what is the difference between arithmetic and geometric sequences? Really comes down to what is that repeated process that we're doing every time. If that repeated process that we're doing every time is addition or, I guess, subtraction, you can think about it that way, addition or subtraction, then it's arithmetic. If the operation we're doing every time is repeated multiplication, and you can kind of think about division fitting under that umbrella, then it's geometric. And so both of these have a repeated process, but the difference between them is that repeated process is different. It's either an operation of addition or an operation of multiplication. So that's how we can kind of think about that. Number 4, is this a function? Back in Unit 1, we talked about why things are either functions or not functions. And in that unit, we talked about something called the vertical line test, But really it comes down to the definition of a function in that every single input has exactly one output. So our inputs are along the x-axis here. So we're inputting all of these values along the x-axis, and it should be attached to or tied to only one value, one y value. So every input has exactly one output. So does every input here, as we go along here, does every input have exactly one output? So for example, -10 has an output right here. That's the only output. There's no other point at -10. And at -5, this one here. At 0, we have an output up there, a y value of maybe, I don't know, 3 or something. But as we go along here, every input only has exactly one output. And so therefore, this is a function. If we were to have something that would kind of bend back on itself here, do this maybe green here. If it were to maybe go along here, and then it kind of came back on itself a little bit for, even just for a moment. These inputs here have multiples. So this input right here of -1, for example, has 3 different y values associated to it, and so it makes it not a function. So every input has to have exactly one output. Number 5, write a recursive formula for the sequence in number 1. So going back to number 1 up here, we talked about this being the first term, and then we're adding 2 each time. That's the common difference there. So if we write it recursively, that would be a sub n equals a sub n minus 1 plus 2. So we're saying any term called n, call it n, is the term before it, term n minus 1, plus 2. So it's the term before plus 2 every time. Term before plus 2 every time. So basically we're saying, this is a fancy way of saying add 2 every time. We would also need to say that a sub 1 is -3 in this case. Just telling it where to start. And then from there, that recursive sequence takes over. All right, so let's get into our lesson for today, which is about writing linear functions and interpreting those parameters of the linear functions that we come up with. So we did something very similar in the last unit where we had an arithmetic sequence and we tried to figure out an expression or equation that was, or formula that could be used to describe that sequence. Same thing here today. We're gonna have one little bit of a difference, but overall the same process. An arithmetic sequence is very similar to a linear function. They're really one and the same. So we're going to talk about the difference between them today, but they're very, very similar. All right, so let's look at this example here. We have a consultant earns a flat fee of $25 plus $40 per hour for a contracted job. Write an equation that produces the total cost for hiring this consultant for X hours. So if you remember from arithmetic sequences, we can do a lot of different things here. We can create a table of values. We can think through like what's constant and then what like adds every time we increase the number of hours, that kind of thing. If we maybe do a table here real quick. So we have hours, and costs. So for 0 hours, the cost would still be $25 if we haven't worked any hours at all. For 1 hour, so not only do we have that 25 flat fee, but we also have an additional $40 for that first hour that we've worked. And then we can continue on. 2 would be 25 plus 40 or 40 times 2, and so on and so forth. So the next one would be 40 times 3. So what's happening here is for every increase in hour, we're adding another $40. We're adding another multiple of 40. And so what we can do is we can write this in general. So let's say we go down to the X hour. So it'd be 25 plus 40 times X, or 40X. So in general, our formula here for the number of hours would be Y equals, for Y is the number of hours, equals, and I'm going to switch the order here, 40 x plus 25. And you can check this just to make sure, but we can actually use this formula to even go down to fractions of hours if that situation allowed for it. So we could do half hours, 3/4 of an hour, something like that, because now we have a formula that would do that. And the difference between, so if we go back to sequences and think about what the difference is between sequences and linear functions, really the only difference is a sequence. So let's see if we have y-intercept, we'll say this is 25 here, and then if we go up to the next value would be 65 at 1 hour. And so if we think about what would happen here with these hours, they would increase, something like this. And so if we work 0 hours, we get $25. 1 hour would be 65. 2 hours would be 105. And we would just keep going like that. The difference between an arithmetic sequence and a linear function is that an arithmetic sequence is what we call discrete, meaning there's just points. There's just random, not random, but like sole points here. It's not one continuous line. And what a linear function is. So if we were to connect these dots, and let me do green here. If we were to connect these dots to form what we call a linear function, this function would go forever and ever in both directions. Technically, this part of the graph wouldn't apply to this situation because we can't work negative hours. So I'm going to take that off. But a linear function is continuous. It's continuous, meaning I can look at maybe 0.6 hours and I've got a point there. I can tell how many that is. Whereas if you think about arithmetic sequences, as we did last time, you might have just terms. Like if we go back to the warm-up here, there's just terms here. We don't have you can't have like a 1.6 term. It's just a list of numbers. So you can't have fraction terms in that sequence. And so these are just discrete, right? If you were to plot these, it would just be a set of points, not a continuous line. And so that's the big difference. But the math equations and the formulas that we use are exactly the same. Sometimes we use different symbols, that kind of thing, but the process of this idea that we can either have a constant, so this 25 is constant no matter how many hours we work, and then we have this additive change for every increase in hour, that stays the same. Okay? So if we were to write the explicit formula for this, it would be exactly the same mathematically. So a sub n equals the first term. So the first term is when this is 1, the first term would be 65 plus 25 times n minus 1. So these are actually the same mathematically. So if we distribute the 25, let me show you this real quick. So 25 times n will be 25n. 25 times negative 1 would be negative 25. A sub n equals, so now you can add the 65 minus the 25 would give you 40. I'm sorry, this should have been 40 here. Because we're adding 40 each time. So the common difference is 40. Apologize. So then we can subtract 65 minus 40 is 25. And then we have the 40n, so 40n plus 25. Exactly the same as the one up here. A sub n is like the output, it's the y value. N is the input or the X value, but it's exactly the same. Just one is discrete, only integer inputs. So you can input 1, 2, 3, 4, 5, 6. Whereas a linear function, you can input anything. Decimals, fractions, integers, zero, whatever you want. You can input into that. Okay, so let's go on to the next one. So Sarah is pumping gas at her local gas station. The cost per gallon of gas is $2.30. Sarah buys a snack for $4, then pumps gas. As she watches the number of gallons of gas being pumped into her car increase, she wonders, is there a function that represents the total amount I will spend at the gas station? So let's help her. Let's help her out here and see if we can come up with a function that would represent total cost as that gallons of gas that she's pumping into her car increases. So part A says, does the price of her snack depend on the amount of gas she pumps? Because that's what's changing, right? Is the amount of gas she pumps into her car. And obviously, the answer to that question is no, right? The price of her snack does not increase based on how much she pumps into her gas tank. So we're going to say no, and it will always be $4, right? The snack will always be $4, no matter what. That's our constant. That's our starting value or initial value. So that will be, if we think about our linear functions here, that's going to be the value on the end that we add to this constant rate of change that we're going to describe with the gas. So we're going to have, we're going to output the number of dollars here, and it's based on $4 plus whatever we get charged for gas. And so for every gallon we pump, so we're going to call that X. X is the number of gallons we pump into the car. That's going to cost an additional $2.30. So if I pump 1 gallon, then that's going to be $2.30. If I pump 2 gallons, it's going to be $4.60, right? And so I'm just multiplying the number of gallons times $2.30. So the number of gallons, X, times $2.30 will give me the price for gas. So this is the price for gas right here, plus the price for the snack equals the total cost. But again, the total cost only depends on, or only changes based on the number of gallons we input. This $4 is constant no matter what. So this is our initial value, starting value, our constant, whatever you want to call that. And then this is the amount that increases per gallon of gas. All right. So if we think about these linear functions, again, same as an arithmetic sequence. Just we can put in a half gallon or a fourth gallon, whatever there. It's not just a list of numbers. Let's move on to our next example here. A radio station starts with a certain amount of money and gives away the same amount each hour to their listeners. What do you think the function below represents? So take a second to do that. Okay, so we start with a certain amount of money. So that's our starting value or initial value. And we've talked about that before, right? That's always going to be represented by the number that is not multiplying by X or anything like that. It's just a constant value here. So we're starting with $2,100. And then this negative 30, what do you think that represents? That represents the amount of money we're giving away. So it's minus because we're giving it away. But we're giving away $30 per hour to our listeners. And so that's what that represents here. So per hour. So that means X is the number of hours that we've gone through on our radio station. So if we were to input here, let's say 4 hours. So that's going to be negative, 4 times 30 is 120 plus 2,100. And we can figure out how much money we have left after 4 hours. So that's going to be, let's see, if we take 2,100 minus 100 would be 2,000, minus 20 more would be 1,9 would be the y value. So this is the amount of money, y is the amount of money left over after X hours. So in this case, 1980 is the amount of money left after 4 hours. So, but we could, technically if we're like consistently giving this money out, maybe, at a more steady rate or something, we could maybe do, per minute or something like that. But in this case, it's just every hour. We don't know exactly how much we're giving per minute or anything like that. But per hour, we know it's at 30. And so we can describe it that way. All right, next one. Suppose that the water level of a river is 24 feet and is receding at a rate of 0.75 feet per day. Write an equation for the water level after X days. How would your equation change if the water level was increasing at a rate of 1.3 feet per day? So take a minute, see if you can do that. Okay, so in this one, again, if you think about our constant rate versus our value that's changing every day, there's a difference here, okay? So 24 feet, if we circle that here, that is our initial value, our starting value, or our constant rate, or our constant. So we're going to start with 24, and that's going to be the same no matter how many days we've gone. That's always going to be the case that we started at 24. It's not always going to be at 24, but it's always going to be the value that we started at. And then we're losing, because it's receding, we're losing 0.75 feet per day. So it's going to be negative 0.75, and then we'll lose that amount every day. So we're going to put X there. Negative 0.75 times X equals Y. So we've got negative 0.75 we're losing per day. So after 1 day we lose negative 0.75, or we lose 0.75. 2 days we lose a foot and a half, and so on. So that would be our equation for the first scenario there. Now what would change if it was instead increasing at a rate of 1.3 feet per day? So think about that. What would that be? In this case, it would be y equals, still starting at 24 feet, but it's going to be a positive 1.3x, because now we want to increase. So for every additional value of x here, we're going to add 1.3. So it'd be, if this is 1, it would be 1.3. If this were 2, it would be 2.6. If this were 3, it would be 3.9, and so on. And so for every additional day, it's going to increase at 1.3 feet. And so that's how that would change. The 24 would remain the same. That does not change in this case. All right? So hopefully that gives you a good idea of how we can write linear functions and interpret their parameters. So we have really two main parameters in a linear function. We have the slope and we have the constant value, or the rate of change and the initial value. And so those are the two main parameters. One of them stays consistent, constant throughout, whereas the other one changes based on increasing number of your input value. And so those are the two main parameters there. So I hope that gives you a good idea of how to write those. All right, in our next video, we're going to talk about more linear expressions and how to interpret those maybe in a real life context and compare those numerically. So hope you'll join us then.